Lesson 12.1, we're going to be on the front page. Remember, read directions that it gives you. So Allie spins the spinner and draws one card without looking. She gets a 3 on the spinner and a 3 card. Then she sets the card aside, spins again, and draws another. So on this first one, it says, is it possible for Allie to get a 3 on her second spin? So if she spins this again, is it possible to get a 3 again? Yes. Is it possible to get a 3 on her second card? Remember, she sets the card aside. No. Right, the card's gone out of the picture, so is it possible for her to get a 3 on the second card? No. On the second one, it says, how does getting the 3 card on her first draw affect the probability of getting the 2 card on her second draw? So it's going to give her a better chance, right? What was the probability of drawing a 2 the first time? 1/4. Without the 3 in there, what's the probability of drawing a 2 now? 1/3. So if you remember, this goes to 25%. This goes to 33%. So are the chances of drawing a 2 higher? Yes. Okay. This is where I'm actually going to have you take some notes. We are going to talk about mutually exclusive. Okay, so go ahead and we're going to write some definitions. Write down mutually exclusive. Okay. What it means for 2 events to be mutually exclusive is that there is no overlap. Okay, and what I mean by that, there are no things in common. No things in common between 2 events. Okay, so that's mutually exclusive. There's no overlap. They have nothing in common. So as an example of mutually exclusive, okay, if I said I roll an even, so we're still thinking about that standard dice, 1 through 6. Okay, if I roll an even, or I roll a 3 or 5. Okay, we have 2 possible outcomes here. What is the probability of rolling an even number? 3 out of 6, right? There's 3 even numbers out of the 6 total. What is the probability of rolling a 3 or a 5? That'd be 1 out of 6 for both of them, but what if I can roll a 3 or a 5? That's 2 out of 6. Okay. Now we're going to compare both of them together. Do these 2 events have anything in common? Why do you say no? You're correct. Because 2 and 3 are not, 3 and 5 are not even numbers. So they have nothing in common. Okay, so what we do now is we can just add these 2 probabilities together. So I take 3/6 plus 2/6. Oh, let me write it this way. 3/6 plus 2/6. Remember, when you're adding fractions, you keep the common denominator. What's my denominator? 6. And then you add the numerator together. 3 plus 2? 5. So the probability of rolling an even or a 3 or a 5 is a 5/6 chance of doing that. Okay. Now, let's do an example of not mutually exclusive. So not mutually exclusive, what does it mean if 2 things are not mutually exclusive? They overlap. Yep, they overlap. Or think they have things in common. So an example I can give for that one is, let's say we roll an even, or a 1 or 2. So we have 2 events going on, right? Let's talk about this. What is the probability of rolling an even? Still that 3 out of 6, right? What is the probability of rolling a 1 or a 2? There's 2 options, so I have 2 out of 6. Is there overlap between them? What's the overlap? The 2, right? 2 is an even number. So what we do, we would still add those 2 probabilities together, but we want to subtract or take out what they have in common. What is the probability they have in common? We said that 2, right? So that's a 1 out of 6 that they have in common. Okay, that 2 is what they have in common. That's a 1 out of 6. Okay, so again, when we add or subtract, we keep that denominator, and then we add or combine the numerator. So 3 plus 2 is 5 minus 1 is 4. What do we always need to do with our final answers? Simplify. So if I divide both these by 2, I end up getting 2 out of 3. Okay. So comparing what we had here with our mutually exclusive and not mutually exclusive. So mutually exclusive, we said 2 events have nothing in common. So when they have nothing in common, we just do what we were doing the other day, and we just add their probabilities together. Okay. However, if they are not mutually exclusive, so they do have overlap, we have to take out what they have in common, so we don't account for it twice. Does that make sense? Okay. So let's take a look at this example here. So the box contains 100 balls. So usually whenever I get something out of a problem, I go label it. So the total, or T, equals 100. So we have a total of 100. And then it says 30 of the balls are purple. So I'm just going to use P for purple. There's 30. And then O for orange, there is 10. I'm going to put that there so it doesn't look like a 0. If you select one of the balls at random, so what does it mean by at random? You're not looking, okay? There's nothing that you are doing to monopolize what's happening. It says, what is the probability of each of the following events? So this one says, what's the probability that the ball is purple or orange? What's my total there? 40. Right, purple and orange, if I add those together, I get 40. What's the total? 100. Out of 100. Yep, so 40 out of 100. And remember, we reduced that. So we divide both these by 20 to get that 2 out of 5. So that has a 2/5 chance of drawing a purple or an orange. That second one says, what is the probability that the ball is not purple and not orange? Right, we take the total and subtract the 40 off because everything else is not purple or orange, right? So what's 100 minus 40? So we get 60 out of 100. Again, we always want to simplify our final answers. So this one I would get 3 out of 5. Okay. I want to ask you something. What do you know about those two right there? They have the same denominator, okay? They have the same total. What else? Maybe even ask, what do you notice about these? They add up to, the numerators add up to 100. So if I added, I'm going to take these. If I took 2/5 plus 3/5, what do I get? I get 5 over 5, which 5 divided by 5 is 1. Okay, so your probabilities, okay, what this is called is the complement. Go ahead and write this definition down. Complement. Okay, how I'm going to describe the complement to you, it's the not of what you're looking for. So it's the other side outcome of event. Okay, and what you should realize about the complements is they should always add up to 1. Complements should always add up to 1. Or if you're thinking about percentages, those would add up to 100. So if I can mark this for you. If you're talking about fractions, they should add up to 1. If you're talking about percentages, they should add up to 100. Okay. So I'm going to ask you an example question here. What is the complement of 2/7? How would I figure out the complement of 2/7?
7 minus 2.
Okay, where did you get that from? Like, where'd you get the 7 from? 7's the total. So remember, if we're thinking of the complement, so I'm going to say probability of the complement. Okay, we know we want to add up to 1, right? So I'm going to take 1 minus whatever the probability I have right now. Okay, so I'm going to take 1 minus that 2/7. Okay, can I easily subtract those right now? One's a whole number, one's a fraction. That kind of makes it tricky, right? How can I make these the same? I could do 1 over 1, but notice their denominators aren't the same. I can change this to 7 over 7 because what is 7 divided by 7? 1. Okay, so that gives me that 1. And then I can now subtract off that 2 over 7. So remember, keep your same denominator. And then what's 7 minus 2? 5. So the complement of 2 sevenths is 5 sevenths. What do you notice between the complement and what we started with? If we add them up, we get that 7 sevenths or 1, right? So if the numerators, to find the complement, you want your numerators, 2 and 5, to add up to your total amount, which would be 7. Okay. Okay, we're going to talk about independent and dependent, the difference. Okay, we kind of talked about this yesterday. What does independent mean? It doesn't affect the second one. So, for example, if I draw a marble out of a jar and I put it back, does that affect the second draw? No, because it's the same as the first, right? If I draw that marble again and I leave it out, does that affect the second one? Yes. Okay, so let's recap these for a second. We have a box of 10 cards. 5 are red, 5 are black. So a card is chosen at random and then replaced. Another card is chosen. Does the color of the first card chosen affect the possibilities of the second card chosen? No, because it was replaced, right? So are these independent or dependent events? That was independent because it didn't affect. Okay. Second one, it says a card is chosen at random and not replaced. Another card is chosen. Does the color for the first card chosen affect the possibilities of the second card? Yes. So are those independent events or was it dependent? Those are dependent events. Yep, because it changed the possibilities of the second one. Okay, last thing we're going to talk about here is we're still going to be talking about those independent events, but we're going to talk about how they relate to each other. So if I give you a dice or a quarter, do those have anything related to each other? Right? They're different objects, right? One's a dice, one's a quarter. If I roll a dice, does that affect what happens with the quarter? No, or is it vice versa? If I flip a coin, does that change the possibilities of rolling a dice? No. So do you agree that these are both independent events? Okay, so go ahead and write on your paper so you can refer to it. Write a dice and a quarter. Okay. We just determined that these are independent of each other. Okay. So I'm just going to give us an example here. What is the probability of rolling a 4? Now let me talk about this notation real quick. It could get pretty daunting to keep writing words like what is the probability of 4. Okay, if you ever see this notation here, that P stands for probability. Okay, let me label that for you. That P stands for probability. And this, what's in parentheses, that stands for the event that's happening. Okay, so on this one, what is my probability of rolling a 4 on a standard dice? 1 out of, what's the total? 1 out of 6. So there's one chance for me to roll a 4 on that dice. Okay, what is the probability of me flipping a heads on a quarter? 1 out of 2, right? Okay, and we said these are independent events. So we want to know what's the probability of doing both of those at the same time. So what we do to figure that out, we take both of their probabilities and we're going to end up multiplying them together. So we're going to take 1/6 times 1/2 because they're independent events. Now remember when we multiply, we're going to multiply straight across. So I'm going to take 1 times 1, which is 1. And then on the bottom, I'm going to take 6 times 2, which is 12. So the probability of doing both of those at the same time is 1 out of 12. Is that very likely? No, that's not very likely to do that. Okay, but the probability of both of those happening at the same time is 1 out of 12. All right, example 4, it says you spin the spinner 2 times. Spin the spinner 2 times. Assume that the probability of a blue each spin is 1/3. Underline that. So probability of a blue is 1/3. Okay. Probability of an orange is 2/3. Says, what is the probability of getting the same color both times? Okay, so there's a little thing we have to do. If we get the same color both times, what are, like, I'm going to rephrase. We can either get blue twice or we can get orange twice, right? So let's talk about the blue for a second. So what's the probability of rolling a blue the first time? 1/3. Okay. What's the probability of rolling blue the second time? Did it change anything about the blue on the spinner? No, so it's still that 1/3, right? Were these two events independent of each other? Or were they dependent on each other? Independent. Okay, so these are independent events. What do we do to find the probability of an independent event? We got to multiply those two together. So if I take 1/3 times 1/3, remember, multiply straight across. What do I get? Careful, 3. Yep, I get 1/9. So I have a 1/9 chance of spinning blue 2 times in a row. Okay. Now, we have to do the same thing for orange. So what's the probability of spinning orange the first time? 2 out of 3. Yep. What's the probability of spinning orange on the second? Still 2 out of 3, right? Why are these the same? Even though one's the first, one's the second? They're independent, right? Because the spinner doesn't change throughout the whole thing. So these, again, are independent events. What do we do to find the probability of independent events? Take 2/3 times 2/3. So on the top we get 4, on the bottom we get 9. Good. Which one do you have a better chance of spinning twice in a row? The orange, right? The 4/9. It wants to know the probability together of that chance happening. So how do we get the probability together, do you think? If I have this for the blue and this for the orange, how do we find the total probability? We're going to add them together. Yep, take that 1/9 plus 4/9. Now remember, when you add, you keep what? You keep the bottom if it's the same. So in this case, we have 9, and then add the top, we get 5. So we have 5. We have a 5 out of 9 chance of spinning the same color twice. I'm going to ask you this. Little recap. How can I turn this into a percentage if I wanted to? Right, I would take 5 divided by 9 in your calculator, which that would end up giving you a 0.56. And then to turn that into a percentage, like you said, we multiply that by 100. So the percentage of this happening is 56%. Okay. Is that very likely to spin the same color twice? Yeah, right? It's about 50%, but it's still a pretty low percentage, right? Awesome.